Ortho-Para directors versus meta-directors is going to be the topic of this lesson. We're going to take a look at EAS reactions for substituted benzenes. And when you've already got a substituent on benzene, it gets to decide where an EAS reaction will happen. So there are some substituents that direct EAS reactions to occur ortho or para relative to themselves. We call them ortho-para directors. And there are other substituents that will direct EAS to happen at the meta position instead, and we call those meta-directors. We'll also compare relative rates of EAS reactions based on the substituent attached, and we'll talk about activating groups, which speed up EAS reactions, and deactivating groups, which slow them down. And we'll also talk about it in the context of electron-donating groups versus electron-withdrawing groups as well. Now, this lesson is part of my organic chemistry playlist. I'm releasing these weekly throughout the school year, so if you want to be notified every time I post a new lesson, subscribe to the channel and click the bell notification. All right, so right off your study guide here is this big, lovely list of substituents you might have on your benzene ring. And we've got them broken up in a couple different ways. So one is electron-donating groups, and the other is electron-withdrawing groups. And that's blue versus red. And notice hydrogen's right in the middle. And so if you got just plain old benzene, it's just got all hydrogens. So everything's relative to hydrogen. So if you're more donating than a hydrogen, you're a donating group. And if you're more withdrawing than a hydrogen, then you're a withdrawing group. And we'll see how these electron-donating versus withdrawing categories will affect the rate of reaction here first. And so first question we want to do is actually just compare relative rates of reaction. And so you just got to remember that in an EAS reaction, benzene's job is to act as the nucleophile. And the higher energy its electrons, the more reactive it's going to be as a nucleophile. The lower energy and more stable its electrons, the slower it's going to be, or the worse it's going to be as a nucleophile. And so it turns out that electron donating groups raise the energy of the pi electrons in your benzene ring. And so they speed up EAS reactions. So as a result, we often refer to these also as activating groups. Now we got to be careful with that little designation here because we can always call them electron donating, it turns out. But whether or not they're activating depends on the type of reaction you're doing. And we usually bring this up in the context of EAS reactions. And sometimes that's the only context we talk about them in. But the truth is we can talk about them in other contexts. In fact, at the end of this chapter, we'll talk about them in nucleophilic aromatic substitution, NAS reactions, and we'll see this opposite designation. So when I call these activating groups, that's only for EAS reactions. We'll find out with NAS reactions where benzene is actually acting as the electrophile rather than the nucleophile, we'll actually find out that the electron donating groups will be deactivating. But in the context of EAS reactions, yes, these electron donating groups are activating. They speed up the rate of reaction for a benzene ring. So whereas these electron withdrawing groups, these are actually going to end up being deactivating. So deactivating groups in the context of EAS. But again, we'll switch which is activating, which is deactivating, say if we talk about NAS, or say maybe we talk about the relative rates of reactivity for the carboxylic acid derivatives later on in the course. So we'll see the switch designations. But these are always electron donating, these are always electron withdrawing, but whether or not they're activating or deactivating is going to depend on the reaction. But for a while now, we're just going to be focusing on EAS, and so I'll be referring to the electron donating as activating and the electron withdrawing as deactivating. But I just want to make it clear that that's specific to EAS. All right. So the bad news is you've pretty much got to memorize this lovely chart. And again, it's on your study guide there, but you've got to memorize it, but we're going to make it make some sense in a little bit. So how you identify something as electron donating versus withdrawing. But what's nice is this is the same chart we got back in the alcohols chapter when we were looking at the acidity of phenols. And we found out that, yep, same exact electron donating group we dealt with back there. And we found out that these actually made acids weaker because they made the corresponding conjugate bases stronger. And so the key is I want to focus on, they make the conjugate bases stronger. Well, now we're talking about benzenes acting as nucleophiles, which is kind of like a Lewis base. And so if they make Bronsted bases stronger, they also make Lewis bases stronger as well. And so these increase the strength of a nucleophile, speeding up a reaction. And so in this case, any one of these groups is going to react faster than plain old benzene, faster than if you just have a plain old hydrogen in that position. And so if we look at any of the ones up here, if we want to compare the relative rates of reactivity, any of them with one of these in blue is going to speed it up and react faster than plain old benzene. And so we can see that we've got an OCH3, that's an example of an OR group there, so just an ether we see there. And then we've also got this ethyl group right here, and that ethyl group is just an example of an R group. So we find out not only is this chart helpful in terms of identifying who's donating and withdrawing, but also degrees of donating and withdrawing. These donating groups get more donating as you go to the left. And so all these what we call pi donors, we'll figure out what that means in a little bit, but all these pi donors are going to be stronger donating groups than just these sigma donors. And so this R group right here, that's just the ethyl, is not quite as donating as the methoxy group right here. Now, in addition to that, there's also a degree of reactivity vertically on this chart in a couple of places. Here, as well as here, as well as here. Now, not so much either here or here, it turns out. So, but here it turns out reactivity is going to increase going up, and we'll find out why that is a little bit later here as well. So, but so far, as we can see it, with only 2 of these actually having donated groups, these are going to be the top 2 in reactivity. And so this would be number 1 with the strongest electron donating group, and this would be number 2 with the second strongest electron donating group. Now, same thing over here. The electron withdrawing groups get more withdrawing as you go this way. And whereas a donating group raises the energy of the electrons of the nucleophile, making it more reactive, so your electron withdrawing groups lower the energy of the pi electrons in benzene, making it a weaker nucleophile. And so in this case, it turns out, again, we have electron withdrawing groups that are increasing in their withdrawing ability going to the right. And so the further you go to the right here, the more withdrawing it becomes and the less reactive that benzene becomes. And so the least reactive are going to be somebody with one of these kind of substituents. And then we've got these moderate withdrawing groups, which are all carbonyls, whether it be like a ketone aldehyde or carboxylic acid or an ester. So, and then we've got the halogens, which are the weakest withdrawing groups and the weakest deactivating groups. And so if we look at what we got left here, we've got a bromine, which is right here. We've got a ketone, the carbonyl of a ketone. You always want to focus on the atom directly attached to benzene, but the carbonyl of a ketone right here. And then we've got the NO2 group right here, a strong withdrawing group. And so we've got a weak one, a moderate one, and a strong one. And again, so the further you typically go this way, the more reactive the benzene. The further you go this way, the less reactive the benzene in an EAS reaction. So in this case, the halogen's going to be next. So then our carbonyl as a moderate withdrawing group. Next, and then finally the nitrogen group, the strongest withdrawing group, makes this the least reactive and therefore the slowest to react in an EAS reaction. So we've just compared relative rates of reactivities. We've did it with very little understanding. It's simply pure memorization of this chart, which will tell us the orders of reactivity in a typical EAS reaction. So, but we've got some more understanding to derive out of this chart. So let's take a little bit deeper look at what makes something a pi donor versus a sigma donor, and what makes something a withdrawing group and things of that sort. So it can help you memorize and identify these different groups. So we're first going to take a look at an Ortho-Para director, and that's just a hydroxyl group here. And we're going to take a couple different views at why we could view him as being an Ortho-Para director. And so one of them is just looking at some minor resonance contributors to him as a reactant. And so in this case, we call him a pi donor because he can donate his pi electrons into the ring. And so lone pair becomes a pi bond becomes a lone pair, typical kind of pattern in resonance we saw for resonance stabilization of lone pairs. Now let's take a look at all the different resonance structures we got here. Okay, but these are one bond away from these pi electrons, so we'll expect more resonance. Lone pair becomes a pi bond becomes a lone pair. But yet again, lone pair is exactly one bond away from more pi electrons, so we should expect more resonance. Lone pair becomes a pi bond becomes a lone pair. Okay, so there's our resonance contributors, and what we can find is that you've got a partial negative charge on 3 of the carbons in the benzene ring. So you've got it on the adjacent carbon to the left, that's one of the ortho positions, if you recall. So you've got it on the exact opposite carbon, that's the para position, and then you've got it in the other ortho position as well. And so in this case, you've got a partial negative charge on these 3 carbons. In fact, let's just kind of highlight those: partial negative, partial negative, partial negative. And what that means is that the energy of the electrons on those three carbons, there's more electron density on those three carbons, meaning this molecule is more nucleophilic on those three carbons. And that's one way to look at why this hydroxyl group ends up being an ortho-para director. It raises the energy of the electrons specifically on those three carbons, making it a stronger nucleophile specifically on those three carbons. Now, one thing we should note here, if we kind of take a look at plotting a reaction coordinate diagram here for just the first step in an EAS reaction. So, and when I say first step, I mean of the EAS mechanism itself, not the formation of the electrophile, but just when we attack it. And so in this case, it is a very endothermic step. And so we got to ask ourselves, how does the impact of one of these ortho-para directors, which in this case, all the ortho-para directors we see over here are going to be activating groups, but these four over here would be deactivating groups. So I first want to just take a look at what if they're the activating sort? What if they're electron donating groups, just like this OH? What effect do they ultimately have? Well, in this case, it turns out it depends on where they actually react. And so it turns out, compared to plain old benzene, so the OH group would actually direct EAS to happen at the meta position with a lower activation energy. And so it turns out it looks like it activates the meta position, even though we just said it's an ortho-para director. Okay, well, the reason is, ultimately, because it activates the ortho-para even more. And so it turns out that when you've got one of these electron donating groups attached, it activates EAS reactions at every position. It just activates it at the ortho and para positions more than the meta. And so one big takeaway, that's why it ends up being an ortho-para director. It's not that you get zero meta product, but you get very little meta product when you've got one of these ortho-para directors attached. And specifically, we're talking about, again, about the electron donating ones, where they activate all the positions as well. They are faster than plain old benzene at any position, but especially fast when substitution happens at the ortho and para positions. All right, so next we're going to take a look at this from a little bit of a different perspective. Instead of looking at the resonance stabilization of the reactant, we're going to take a look at the sigma complex intermediate and look at some resonance stabilization for it. So specifically, we're going to have substitution occurring at the ortho position, one of the activated positions for the OH, or the most activated. Okay, so I've got the electrophile attached at the ortho position, which leaves the carbocation here on the other side. And then we've got some resonance structures we can show here. One bond away there, so we'll move those over. But we're still one bond away from pi electrons, so we'll move these over here as well. All right, so we got our standard 3 resonance structures with any EAS reaction for the sigma complex. But with one of these pi donors, you're going to get one additional resonance structure. So because you've got an atom with a lone pair, and you'll end up with the positive charge right next to it, provided substitution occurs at the ortho or pair positions anyways. We'll find out it doesn't happen at the meta. So, but the carbocation is going to end up right next to it in one of the resonance structures here. And so we get one additional resonance structure. Okay, and so we might be like, well, it's just one additional resonance structure. We already had 3, but now we got 4. However, big deal here is that this is the major resonance contributor. So in all these other resonance structures, you've got a carbocation, which does not have a filled octet. Here, the cation's on the oxygen, which still has a filled octet. And so this is a more stable structure. The other way you could look at this is here we've got the 2 lone pairs on the oxygen and then 2 pi bonds. Same thing here and here. But now we've got 3 pi bonds, only 1 lone pair. And with more electrons and bonds, another evidence that it's the most stable of the resonance structures. And so we didn't just get like one more little tiny resonance structure. We got one more that ends up being the major. And it turns out that as a result, so phenol here is probably, I don't know, 100,000 times more reactive than plain old benzene in a typical EAS reaction. So a significant increase in reactivity for one of these pi donors. Now that's in the case of like, you know, a hydroxyl group or an ether here. So, but it turns out nitrogen is even a stronger donating group, like with a NH2 or NR2. And in this case, with nitrogen being less electronegative, it donates even more strongly. It's not holding on to its electrons as tightly, if you will, so more willing to donate. The other way you could look at it is that your major resonance contributor would put the positive formal charge not on an oxygen, but on the less electronegative nitrogen, which all things being equal would be a better place for it. And so a couple different ways you could look at why the nitrogens end up being stronger electron donating groups than the oxygens. Now in the other case though, there is a nitrogen down here that is a weaker donating group than these oxygens, and that's the nitrogen not of an amine like here, but the nitrogen of an amide. And so the key here is that in addition to donating these electrons to do resonance with your benzene ring it's attached to, well, instead you could also do resonance going the other direction with the carbonyl. And as a result, because you can do resonance in either direction, well, then overall, then it's going to be less donating towards the benzene ring because you can donate it towards the carbonyl on the other side instead. And so as a result, it's just not overall as strong of an electron donating group toward the benzene ring, which is ultimately what raises the energy of the electrons in the benzene, making it a better nucleophile. So cool, when you're trying to identify these donating groups and stuff like that, you always want to focus on the atom directly attached to the benzene. So that's the atom of focus. And in this case, it was an oxygen with lone pairs. Yep, that's one of these. Cool. All right, so now we've taken a look at 2 different perspectives of why these pi donors are more reactive. What about the sigma donors here? What if you just have a plain old R group? So, or actually, let's talk about one other thing real quick. Okay, so one other thing, we talked about these also being part of the Ortho-Para directors, and being part of the Ortho-Para directors, the question is why? Well, here I showed ortho substitution. Well, again, had I shown ortho or para substitution, we would have got a 4th resonance structure looking something like this. However, had we done meta substitution, instead of putting the electrophile in one of these 3 positions, how do we put it in one of these 2 positions? Well, let's say you put it in this position. If you put the electrophile in this meta position, then your positive charge ends up in these 3 locations instead in the sigma complex. And because it never ends up on this carbon next to the oxygen, you never get a chance to have that 4th resonance structure. And so you don't get that additional like significant resonance stabilization if you go meta. And so that's why this ends up being an ortho-para director. So you get that 4th resonance structure and a much significantly more stable sigma complex, and therefore a lower activation energy in the formation of that sigma complex. All right, so what about these sigma donors? So they're not doing any resonance per se, but you've just got like, you know, an alkyl group or an aryl group. Well, let's just consider an alkyl group for a minute. Let's just consider what if this, you know, this OH right here had been simply like a methyl group. So let's go and just replace this here with a methyl group. So let's do that across the board here. Let's see what happens. Okay. We'll see why I didn't replace it on the last structure there at the end there, because we're going to erase it. All right, so in this case, if it's just plain methyl group, the question is, why would this want to go ortho or para? So, well, in this case, if you go ortho, again, you're going to get 3 carbons here, this one, and this one. So here, here, and here, that all get a chance to share the positive formal charge and have less electron density in the resonance hybrid. And the key is this one right here. So notice here we have a secondary carbocation, here we have a secondary carbocation, but here we have a tertiary carbocation, which is a more stable carbocation as we learned back in 1st semester. Now you don't get a 4th resonance structure in this case, so we're not even going to get this one here. And so resonance stabilization is typically more important than hyperconjugation, so which we see with carbocation stability, the explanation for that. So this is not as significant of an impact, and that's why it's not as strong of an electron donated group when you just have one of these sigma donors instead. So, but again, increase in carbocation stability. Now the plus charge is shared between a secondary, and a tertiary, as opposed to just like, say, 3 secondaries that have been plain old benzene. And so a little bit increase in stability, and this is still going to react quite a bit faster than plain old benzene, it turns out. All right, so that's our sigma donors. So then let's talk about, say, a halogen here. And halogens are last of our ortho-para directors. And halogens are a little bit funky here. So let's take a look at how these influence some things. All right, so your halogens, pretty darn electronegative, right? Like fluorine, the most electronegative element there is out there. And so we kind of got this interplay because if you look at it, the halogens do have lone pairs. And so you could potentially get an additional resonance structure here. And so just like we did with oxygen here, we're going to get a fourth resonance structure. For our sigma complex. So we do have one problem though, is it's so electronegative, so inductively it's pulling electrons towards it, this fluorine is. And because the ring has a positive charge in the sigma complex, so pulling electrons away from an already electron deficient ring makes it less stable. And so from an inductive standpoint, fluorine's making this lovely carbocation less stable. From a resonance standpoint, it's making it more stable. And the question is, well, which one makes a bigger impact? Well, because we consider it an actual deactivating group for these lovely halogens that are considered these weak deactivating groups, it turns out the inductive effect is more significant than the resonance effect. And so that's ultimately why they're deactivating groups. So notice for nitrogen and oxygen, it turns out that the resonance donating group, or resonance donating ability is more important or more significant of an impact than the fact that they're pretty darn electronegative as well. And so inductively they're withdrawing, but resonance-wise they're donating, and they're more donating than withdrawing. But for the halogens, it's the opposite. They're actually more withdrawing than they are donating. However, their only opportunity to get this fourth resonance structure still occurs if you do substitution at the ortho or pair positions, not at the meta. And so as a result, they're like, well, we're deactivating groups, but we can stabilize the sigma complex a little better if it goes ortho or para, and so they end up still being ortho-para directors. This is worth noting because if you notice, all of these guys over here, all of them, the electron donating groups, they're all ortho-para directors. But for your electron withdrawing groups, most of them are meta directors except the halogens. The halogens are the big exceptions. They're still electron withdrawing groups and deactivating groups. They slow down a reaction. However, they're still ortho-para directors. And so all electron donating groups are ortho-para directors. Most electron withdrawing groups end up being meta directors. The halogens are the big exceptions. So keep that in mind. All right. So that's the halogens, and that's now we've covered all the ortho-para directors. Let's take a look at the meta directors. All right, so now I've replaced the methyl group now with a nitro group, and you can see the big positive formal charge on that nitrogen makes it a very strong electron withdrawing group now. So way over here in the class of the strong electron withdrawing groups. So if you take a look at all your different withdrawing groups, so all your strong ones either have a positive formal charge on the atom that's directly attached, like in the NO2 or the NR3 group, or a significant amount of partial positive due to the electronegative atoms they're attached to. So even the moderate ones are all carbonyls, and having a double bond to an oxygen leaves that carbon with a significant amount of partial positive charge. So always focus in on the atom directly attached to benzene when you're trying to identify your group. So oftentimes with an amide, if you're attached to the carbonyl of the amide to the benzene, well, that's going to be a moderate withdrawing group. But if you're attached to the nitrogen, like in this case, well, then it's going to be a donating group, and definitely one of the more common ones students struggle to distinguish. But always focus on that atom directly attached to the benzene ring. All right, so in this case, I want to show you the difference in terms of going ortho or para versus going meta, because, you know, in the last example we dealt with our ortho-para directors, we saw why the ortho and para positions were so good. We got stabilization of that sigma complex. Well, now with the meta position, we're going to find out why the not why the meta position is good, it's actually why the ortho-para positions are so bad. It's really going to be the key. And so in this case, when we go attack our electrophile, if we do substitution at the ortho position, we can see the 3 carbons where we share that positive charge. So, and right here's the big one here. That positive formal charge is right next to the very electron withdrawing nitro group. And so lack of electron density and the nitro is pulling even more away from it, you know, causing significant destabilization of this sigma complex, raising its energy significantly, making it harder to form. Now that's with the ortho and para positions, you're going to end up with a structure where the positive charge ends up right next to the electron withdrawing group. Whereas if we do the substitution instead at the meta position, so then look at the 3 carbons where your plus charge ends up. it never ends up adjacent to the electron withdrawing group. And so it turns out that withdrawing group is still going to destabilize this sigma complex, just not as much as if we'd done the substitution either in the ortho or para positions. And so again, it's not that meta is so good, it's that ortho and para are so bad. And so if we take a look again in black here, let's say this is the formation of the sigma complex for plain old benzene. Well, now, if you go meta, you can see that the activation energy is higher. This is going to react more slowly than plain old benzene. So, and again, it's not that meta so good, but we can see with OP for Ortho-Para, it's that it's so bad. The activation energy is raised even higher to go for the Ortho-Para position. So when you've got one of these deactivating groups, it turns out it deactivates it at all positions. It just typically, for these guys anyways, the moderate and strongs, it deactivates it the most at the Ortho-Para, which is why by default it ends up just being a meta director. You get very little Ortho-Para product and the majority ends up being meta. Cool. Again, halogens are the big exceptions. Again, it deactivates all positions, but it deactivates the meta more than it actually deactivates the Ortho-Para. So keep in mind, they're the big exceptions. Okay, before we go predicting products, we got one last little thing to show, and that's some special reactivities for aminobenzenes here. So aminobenzene actually has a name called aniline, as we learned in the last chapter, and but it doesn't have to be just plain aniline. It could be a substituted aminobenzene as well. So, but when you've got one of these aminobenzenes, you might recall that amines are bases, and bases react with acids. You might remember that too. And in this case, we might add they can react as a Bronsted acid and get protonated, but they can also react as a Lewis acid. They can react with a Lewis acid, acting as a Lewis base, and end up being one of these structures right here. And in both cases, you got something interesting happening because you end up with a nitrogen with a positive formal charge. And when nitrogen's got a positive formal charge, it actually turns into a strong electron withdrawing group, a deactivating group, and a meta director. Okay, well, that's kind of a problem. So we always, we often look at these as the strongest pi donors on the typical list you guys are presented with. And so they're the strongest electron donating groups, unless you react them with acid. And that's a problem because all of your EAS reactions are typically standardly performed with acid, either Bronsted acid, like say in nitration or sulfonation, where you've got concentrated sulfuric acid in there and stuff, and nitric acid, or with a Lewis acid like AlCl3 or FeBr3, FeCl3 for a lot of the other EAS reactions. And so all of a sudden now we have a problem. We said these are the strongest activating groups, except for all the EAS reactions, it looks like they're going to either get protonated, or at least in the very least, they're going to end up with a positive formal charge and turn into deactivating groups. So oftentimes, we've got to be careful with aminobenzenes. So aminobenzenes, we often leave out any sort of acid catalyst if possible. And what's nice is they're so reactive, they often don't need it anyways. And so in this case, let's say we go Br2 and FeBr3. Well, if we do the reaction here, because there's a Lewis acid present there, first thing that's going to happen is the nitrogen's going to end up bonded to the iron. In this case, instead of to aluminum, it'll be to iron. But that's going to leave nitrogen with a positive formal charge, and as a result, you'd end up with one of these meta directors instead of an Ortho-Para director, and the substitution is going to happen meta. And so what we often do with the aminobenzenes is we just leave out any sort of Lewis acid catalyst in most of the reactions, and they work typically just fine. And so in this case, it now happens at both the ortho and para positions. Cool, so for an ortho-para director, in most examples, you're going to end up predicting both the ortho and para products. We'll see some exceptions to this when we work a few examples and stuff like this. But that's what we mean by an ortho-para director. It directs EAS reactions to happen there. But for an aminobenzene, you can leave out the Lewis acid catalyst. It is so reactive, being the strongest of our pi donors here typically, that it doesn't actually need the Lewis acid catalyst and it'll work just fine. And in fact, again, if we add the Lewis acid catalyst, it'll turn into one of these and substitution will take place at the meta position instead. All right, so let's take a look at our first example of an EAS reaction. In this case, HNO3, H2SO4, you recall, does nitration. We're going to replace a hydrogen with a nitro group, an NO2 group. So first thing to note is when we're doing an EAS reaction, most of the time, you're typically going to assume it just happens once unless otherwise specified. Now, the truth is in the lab, it actually might happen multiple times, especially if you got one of these stronger activating groups attached. That actually might direct it to actually happen multiple times if you're adding excess, reagent, and even if you're not, you might get some mixtures and stuff like this. But however, on paper, typically going to assume that an EAS reaction happens just once unless otherwise specified. So here we're going to do nitration. We're going to do it once. So the group, second thing here is the group that's already attached to benzene, he gets to make the call where EAS happens. It's not the new thing coming on. A lot of students will make the mistake of saying, well, he gets to direct where he goes. No, no, no. It's his house. He's already attached to benzene. It's his house. If you've got a, 5-bedroom house and you live in one of the bedrooms and you take on a new tenant to be a roommate, you get to choose which room they get to stay in, not them. It's your house. Same thing here. So this group right here, that's his benzene ring. He's going to decide where the nitration event takes place. Now in this case, we got to identify what kind of a group he is, and you always want to focus on that atom directly attached, and that is the carbon of a carbonyl, in this case of a ketone, but it's the carbon of a carbonyl, one of these moderate withdrawing groups. So, and in this case, also a meta director. And so he's going to direct nitration to happen meta relative to where he is. And so that's going to either be meta on this side or meta on this side. So, and right now this thing is symmetrical. So whether it happens here or here, it's exactly the same thing. So only one major product to draw here. Cool, so there's our first example. Let's take a look at a second. All right, in this next example, we've got phenol, and we're doing bromination, Br2, FeBr3, and it's the hydroxyl group that gets to decide where bromination is going to take place. And that hydroxyl group, again, if you've got an oxygen or a nitrogen with a lone pair of electrons, that's one of your stronger electron donating groups and an ortho-para director. And so he's going to say, yep, bromination is either going to happen ortho or para relative to where I am. And in this case, both are going to actually take place. And so we'll put him back in his place. And so ortho is one of the possibilities. And para is the other. Now, when you've got an ortho-para director, you're typically going to, in most cases, predict both products. But that doesn't necessarily mean they form in both equivalent amounts or anything like this. So it turns out you've got 2 ortho positions and only 1 para. That gives ortho an advantage. But an even bigger advantage is the fact that the para, these groups are far apart and there's no sterics between them of any speakable amount. But when they're ortho to each other, sterics becomes an issue, especially the larger either of these substituents or both become. And so as a result, most of the time when you've got an ortho-para director, in almost every circumstance, there is one major exception, but almost every circumstance, you get more para than ortho. So, however, typically, unless the groups are really large, if that's the case, you'll draw just the para product. And I'll show an example of that here in a little bit. But if it's not, if neither of them are that large, and we'll talk about how you identify what's that large, typically you're going to show both the ortho and para products and predict both. So in this case, it turns out that, yep, the para would be slightly higher yield than the ortho, but you're going to get a fair amount of both in this case. All right, in this next example, we're doing a Friedel-Crafts acylation, but this is the ethyl group's benzene ring. It's his house, so to speak. And an ethyl group is just an alkyl group, a sigma donor, and an ortho-para director. And so he's going to direct the reaction to happen either ortho or para. So, but it turns out this acyl group, a carbonyl, is an example of a bulky group. And acylations, when you've got an ortho-para director, happen almost exclusively para. There'll be a small amount of ortho product, but not much. So a lot more para. And so this is one example where you're often instructed to predict just the para, even though you had an ortho-para director. Cool, and there's our major product. All right, this next example, we're going to make this a little bit harder because now we've got actually 2 substituents present. And when you've got more than one substituent, well, now you've got potentially a competition. Who wants to direct where? Well, if there's no conflict, if your 2 substituents in this case direct towards the same locations, well, then you don't have a problem. So, and you know where you're going to go. But if there is a conflict, then you've got to have a rule for who gets to decide. Well, the rule typically works like this. If you've got any donating groups whatsoever present on your ring, like we do here. In this case, we've got a methyl group, which is just an alkyl group and a sigma donor. We've got the nitro group, which is a strong withdrawing group over here. So the methyl group is an ortho-para director. The nitro group is a meta director. So if you've got any donating groups whatsoever, like we do, then the strongest donating group wins. The furthest left it is on this chart, so the more likely it gets to be the one doing the directing. Now, the exception to this is what if you don't have any donating groups? What if everything you have is all withdrawing groups? Well, if everything you have is all withdrawing groups, in that one situation, then the strongest withdrawing group is going to get to direct. So but that's it. Even if you have a really strong withdrawing group and a rather weak donating group like we do right here, the strongest donating group wins. So any donating groups present, they get to decide. If there's only withdrawing, does the strongest withdrawing decide? All right. So in this case, we're doing bromination, and let's just see if there's any conflict whatsoever. So our methyl group here, again, being an ortho-para director, says, well, there's my ortho positions, there's my para. So, and in this case, the nitro group being a meta director says either there or there. Well, there's taken, there's no hydrogen there to replace, that's where the methyl group is, so we have to rule that out right off the bat. But there is a conflict, and so we're just gonna rule out this position right here from the get-go. So, because the methyl group is going to get to do the directing. It's the strongest donating group present. Now, any one of these three positions is theoretically possible, but it turns out one of them is not even going to occur. So in this case, there's no symmetry, so it's not like we could say, well, this is the same as this. It is not. So, but this position right here is in between two other substituents. And when that happens, there is a lot of steric hindrance. And if you've got a location in between two substituents, you are not likely to do EAS there if you have any better options. And we've got better options in both cases. Now in this case, if I put the bromine here, it'll be next to the methyl. But if I put it here, it'll be next to the nitro. And so no matter what I do here, it's going to be next to another substituent. So we can't just be like, well, para should beat ortho. Well, not necessarily in this case. So, but we'll predict both products. So one option is ortho relative to the methyl group. And the other option is para relative to the methyl group, and both will occur. But again, that other ortho position, substitution is not going to take place to any significant extent there at all. All right, last example here, and this one's going to be a little bit tricky because we actually have two benzene rings in our reactant. So, and the tricky part is that students typically want to do the EAS reaction once on each ring. But if you recall, the assumption we make is that when you're doing an EAS reaction, you only get to do it once. Not once per ring on your reactant, once per reactant. And so if you've got more than one benzene ring, you've got to react it with the more reactive of those rings, or most reactive of the rings if you have more than two. Well, in this case, we've got two, and we've just got to decide which one's the most reactive, or the more reactive. And so what we're going to do is identify the substituents on these rings as being either donating, and therefore activating, or withdrawing, and therefore deactivating. And so if we look at the methoxy group here, that's one of these lovely, right here, these ethers, oxygen with lone pairs. So it's a pi donor, rather good donating group. So I'll label it with a D for donating. Whereas on the other one here, it's the carbon of a carbonyl that's directly attached to the benzene. And that carbon of a carbonyl is one of your moderate withdrawing groups, and is therefore going to be deactivating in an EAS reaction here. So, and then you could also look at them as being bonded to these separate rings and stuff like that, but because they're both bonded to another benzene ring, it's not going to have a huge impact and not going to be the major difference of comparison. So the difference, though, comes down to a donating versus a withdrawing. And so the donating group is going to make the ring on the left the more reactive one. Now, when I look at this lovely set of rings here, so now we got to decide there are two substituents on this ring, the methoxy group and then this lovely group right here. And so one of them is the aryl group, and then one of them is the methoxy group. And you recall we said that when you've got multiple, at least one of the two of donating groups or multiple donating groups, the strongest donating group wins. And so that's going to be the methoxy group here. And so he does the directing, and he says, okay, relative to me, I'm an ortho-para director. Well, the para is not an option. There's not a hydrogen there to replace. We already have a substituent there, but either one of these orthos could work. And because this thing is symmetrical, it doesn't matter which one we choose. And so when we do chlorination here, cool, then didn't matter which one we choose, exactly the same thing either way, and there's the product that we would predict. Cool, you're definitely going to want to work several examples of this on your own. And the biggest thing is, again, getting this lovely table down. And again, take a big, broad perspective look. Every one of your electron donating group is one of three things. It's either an oxygen or a nitrogen with a lone pair of electrons directly attached to your benzene, or it's just an alkyl or aryl group. Everything else is a withdrawing group, whether it be a halogen, So whether it be a carbonyl, or whether it be an atom with a full positive formal charge, or atoms with significant amount of partial positive charge because they're bonded to electronegative atoms. So those are all going to be your withdrawing groups. And again, all your donating groups are Ortho-Para directors, and most of your withdrawing groups are meta directors. The halogens are the big exceptions. So definitely want to get these down. Now, if you found this lesson helpful, would you consider giving me a like and a share? Best thing you can do to make sure other students get to see this lesson as well. If you're looking for the study guide that goes with this lesson, if you're looking for lots of EAS practice problems, if you're looking for a final exam rapid review or practice final exams, check out my premium course on chadsprep.com.